I'm Paul Dickman, and this is the first in a series of lectures on statistical methods for survival analysis. The target audience of these lectures is students and researchers in biomedical sciences who don't have extensive training in statistics, but have learned some basic statistics, understand the concepts of hypothesis testing and linear regression or logistic regression. So this first lecture, I'll introduce the basic concepts in survival analysis, and in particular the survivor function and the hazard function. We'll then look at how to estimate the survivor function using the Kaplan-Meier method, and how to test for differences in the survivor function using the log-rank test. The slides are available on my website, as is R, Stata, and SAS code available for reproducing the analyses that you'll see in these lecture notes. So first, a little bit about me. I'm Professor of Biostatistics at Karolinska Institutet. My research interests are in register-based epidemiology with a particular focus on cancer epidemiology, and these interests will be reflected in the examples that you're going to see. Stata is my primary software tool, but I'll illustrate how to do these analyses in both Stata and R. Now, I'm going to start with some terminology. And terminology is important because in survival analysis, we can estimate either the proportion who survive or the rate at which one dies. And these two quantities are mathematically related, but proportions and rates are mathematically very different. So strictly, a ratio is the result of dividing one quantity by another. In the sciences, however, it's mostly used in the more specific sense when the numerator and the denominator are two separate and distinct quantities. The numerator is the top bit of the fraction, the denominator is the bottom bit. So the proportion is a type of ratio in which the numerator is included in the denominator. So out of a group of individuals, the proportion who have one characteristic. And a proportion must be between 0 and 1, including 0 and 1. A rate, however, is a measure of change in one quantity per unit of another quantity. A rate must be positive, but a rate can be greater than 1. Now, we often hear people talk about the survival rate of a group of patients over a specified time period. This is the number who survive divided by the total alive at the start. This is not a rate, this is a proportion. And I'm going to try and call it a proportion, although you'll see it very commonly called. So, what is survival analysis? Well, it's the theory and the methods for analyzing time-to-event data. Time-to-event data are generated when the response measured of interest is the time from some well-defined origin of measurement to the occurrence of the event of interest. For example, the time from diagnosis of a disease to death. Now, in survival analysis, the outcome can be thought of as comprising two dimensions. We have the binary event indicator, did the event happen, yes or no, and then we have the time at risk. And this is what makes survival analysis special, is we need to consider both of these dimensions of the outcome. Now, in medical science, we call this field survival analysis, but it's also known as failure time analysis, primarily in engineering, or lifetime analysis, or time-to-event analysis. Now, what can we estimate from time-to-event data? Well, we can estimate the proportion who survive, or the survival probability. The proportion who have not experienced the event at a given point of time during follow-up. Now, this is a function of time. We can also estimate summary measures of this. So, for example, the mean survival time or the median survival time. We can also estimate event rates. at any point in time, what is the rate at which the event occurs. So if the event is death, this would be a mortality rate. If the event was disease incidence, this would be an incidence rate. In this field, we use the generic term hazard. So we talk about hazard rates. Then we can estimate ratios of hazards. And this is a way of comparing the event rates or the hazards between different groups. Now, the characteristic that complicates the use of standard statistical methods is censoring. I'm going to give a more detailed definition on the next slide, but censoring occurs when the survival time is only partially known. Now, if everybody has complete follow-up, then we can ignore the time dimension. For example, when studying 30-day mortality following surgery, we can just study the binary outcome and calculate the proportion of patients who died within a 30-day period. However, if not all individuals have the same potential follow-up time, then we need special methods. For example, if we recruit all patients diagnosed with cancer during a 5-year period from 2015 to 2019 and follow them up for death until the end of 2019, then those diagnosed later will have a shorter follow-up and therefore be less likely to die during the follow-up. So we can't just calculate the proportion who die. We need to take account of both dimensions of the outcome. Did the patients die, and for how long were they at risk, or for how long were they followed up? Now, censoring, we're going to only cover right censoring, which is the most common form of censoring in medical studies. But this is the situation where an individual can no longer be followed up and the event of interest has not occurred. So, for example, if we're studying the survival of cancer patients, then the patients enter the study at the time of diagnosis or the time of treatment in randomized trials, and we'll follow them up until the event of interest is observed. Now, censoring might occur for one of the following reasons. Firstly, termination of the study. We have to stop the collection of data and analyze the study. So any patient, if the outcome is death, then any patient still alive, death has not yet occurred, their survival time is censored. If our outcome is death due to a specific disease, then individuals who die of another cause, they can't die of their disease, we can't follow them up anymore, their survival time is censored. Or if the patient emigrates or withdraws from the study, their survival time is censored. The event hasn't occurred and we can't follow them up anymore. Now, there are other forms of censoring, left censoring, interval censoring, and then related concepts, truncation, left and right, but we're not going to talk about them here. So let's have a look at an example. This is a data set distributed with the survival package in R. It's data on 23 patients diagnosed with acute myeloid leukemia. And the research question at the time was whether the standard course of chemotherapy should be extended, so-called maintenance therapy. So we just have 3 variables in our data set. We have the 2 dimensions of the outcome, the time at risk, and then the status, 1 if dead, 0 if censored. And then we have a binary explanatory variable, which is maintenance chemotherapy, 1 for no, 0 for yes. This is what the data looks like. We have 1 row for each patient with the time, the status, and the value of the exposure. Now, this is the survivor function for these data. So this is the probability of surviving, the probability of not experiencing the event, which is death. So at time 0, everybody is alive. So the survivor function is 1. And as time progresses, the survivor function drops. And I'll go through in detail how we estimate this function. But firstly, a little bit in general. Well, the survivor function, S of t, is a non-increasing function with a value 1 at time 0 and then 0 as time approaches infinity. And we should remember that this is a function. It's a function of time. We can read off specific values of the function of time and talk about, for example, the 1-year survival or the 5-year survival, but the survival function is a function. And non-parametric methods for estimating the survivor function typically involve estimating the survival proportion at discrete values of time and then interpolating these to obtain an estimate of the function. Now, let's imagine we want to estimate 5-year survival, the proportion who survive 5 years or more for the AML data. Now, if we look closely at the data, we can see 18 of 23 patients die within 5 years. But not all of these 23 patients could be followed for 5 years, so we cannot use this as an estimate of 5-year survival. We have a problem with censoring. If we did use this estimate, we would be assuming that all of the 23 patients could be potentially followed for 5 years, and that's not correct. Now, the way we deal with censoring is we chop up the follow-up time into small intervals. So, for example, we can chop up the follow-up time into 1-year intervals and estimate what's the probability of surviving 1 year. And the reason we do this is that we can make assumptions about censoring which are appropriate within small intervals but are not appropriate during long intervals. So we'd estimate probability of surviving 1 year. Then, given that you've survived 1 year, what's the probability of surviving 2 more years? 1 more year. Then, given you've survived 2 years, what's the probability of surviving 1 more year, which is P3. So this is a probability. P2 is a conditional probability. The conditional probability of surviving 1 more year, given you've already survived 1 year. So once we know these 5 probabilities, how do we get the probability of surviving 5 years? Well, we multiply them together, because in order to survive 5 years, you have to survive the first year and the second and the third and the fourth. And so here we have it mathematically. Capital Pi here means product, multiply. You've probably seen capital sigma, which means sum. So this just means multiply together the pi's, where I is 1 to 5. So multiply together these 5 probabilities. So the Kaplan-Meier method, well, what we do, we split follow-up into intervals with a new interval at every event time. So in my outline, I said, well, let's have 1 probability for every follow-up year. What we do in practice with the Kaplan-Meier is there's an interval at every event time. Then we estimate the conditional probabilities of surviving each small interval, and that's just 1 minus the proportion who die during the interval. And typically, there will only be, say, 1 person who dies at each event time. Then we take the product of the conditional probabilities. Now, in theory, survival time is measured with infinite precision. In practice, we don't get that. So in practice, there might be both events and censorings at the same time, as at times 13 and 45 in our example. And if this happened, we assume that the events come first. So that is, the censored observations are assumed to be at risk when the events occur. Now, this is not a good assumption, so we want to avoid data which has lots of ties. We want our survival time to be measured as accurately as possible. So, here we have the data again on the left-hand side, and on the right-hand side, I have the tabulation of the number at risk and the number of deaths, and our Kaplan-Meier estimate of survival. So at time 0, there are 23 people at risk, and the survivor function is 1. Now, the survivor function remains at 1 until there's an event. And the first event is at time 5. There's still 23 people at risk, and we have 2 deaths. So, what's the probability of dying within this interval? Well, it's 2 over 23. What's the probability of surviving this first little interval? It's 21 over 23. So what we do is we multiply whatever the survival function was by 21 over 23. Then the survivor function remains at this value until the next event time, which is time 8. At time 8, there are 2 deaths, so we multiply the survivor function by 19 out of 21. The next time, time 9, there's 1 death, we multiply the survivor function by 18 over 19. So every time that there's a death, the estimated value of the survivor function drops, and then it remains constant until there's another death. It remains constant when there are censorings. So, here is another illustration of this time graphically. So, we always start at time 0, the survivor function is 1. The survivor function remains 1 up until just before time 5. And at time 5, there's 2 deaths. So, probability of surviving this very small interval of time around time 5 is 21 out of 23, because 2 out of 23 died at this time point. So the survivor function drops. Then it remains constant until just before the next death, which is at time 8. And then at time 8, we multiply it by 19 out of 21 because 2 patients died there. Then it remains constant until just before time 9. Then it drops again, and so on. And so here is the estimated survivor function for the entire follow-up. And now we can see at time 16, there was a censoring, but the censoring does not change the estimated survivor function. What it does is it reduces the number of patients at risk, which affects what happens when the next patient dies. So I now have another description of the Kaplan-Meier function. This is in more complete mathematical detail, and I will leave that for you to read in peace. So this is just written down in text what I've explained by looking at the data. This is how we estimate the Kaplan-Meier function in R. We use the surfit function, and in order to estimate survival, we need to tell our software the two dimensions of the outcome, the time dimension and the status dimension. And in R, we do this using the survival object, or serve here. Now, we do something similar if we're modeling with, say, Cox regression, but here we're not doing any modeling, so this will just give us the Kaplan-Meier estimate of survival. And we're storing this in the KM-fit object. We get a summary of the KM-fit object, which gives us our estimated survival function, and we can also plot this KM-fit object. Will give plots. Now, in Stata, what we do is before we do any survival analysis commands, we set up the data for survival analysis using the stset function. So we tell Stata the two dimensions of the survival outcome just the once. So stset is the time dimension and here's the event dimension. So then when we want to do Kaplan-Meier estimates, we don't have to tell the software the outcome again. We just say STS list, and it will give us the Kaplan-Meier estimates, or STS graph. STS graph can produce graphs of many quantities. By default, it's the Kaplan-Meier estimate. So that was the survivor function. Another important function is the hazard function. Now, hazard is just a generic term used to describe the event rate. And the hazard function is also a function of time. This is the instantaneous event rate at time t, conditional on survival up to time t. Now, this is it mathematically. So it's the probability of having an event in the next small instance after time t, given you've already survived up to time t, and then divided by the person time, if you like. Now, the survivor function is cumulative. It describes the probability of not failing before time t, sort of from the start of follow-up, whereas the hazard function is instantaneous. So it focuses on the failure rate at time t among those individuals who are still alive at time t. And a lower value for the hazard rate or the failure rate implies a higher value for the proportion who survive, and vice versa. And as I said at the start of the lecture, the hazard is a rate, not a proportion or probability. So the hazard function can take on any value between 0 and infinity, whereas the survivor function is restricted to the interval from 0 and 1, including both 0 and 1. Now, the hazard is used most when we model. When we fit models in survival analysis, the most common of which is the Cox proportional hazards regression model, we model the hazard function. So it's typical to present descriptive statistics on the survival scale and then model the hazard and estimate hazard ratios. And we'll get to modeling in the next lecture. Now, there is a relation between the survivor function and the hazard function. I don't expect you to understand the mathematics, but it's here for completeness that if we know the hazard function, then we know the survivor function. The two functions are mathematically related. Now, here we have the survivor function as a function of the hazard function. Survivor function is the exponential of the negative of the integrated hazard, or the area under the hazard function. Now, the integrated hazard is often called the cumulative hazard. Now, it's not important that you remember all of these functions and all of these relationships. They're in your textbook or on these slides if you want to look them up. The important thing is that these functions exist and they are mathematically related. So let's have a look at some examples. We'll start with some simulated data and then go on to a couple of real-life examples. So in this one, we have a randomized trial. Patients are randomized to one of two treatments, A or C, and then we have 5 years follow-up. And so the question I'll ask you is, which treatment is associated with the best survival? You can pause the video and think about it. Now, what we see is at 5 years, the proportion who survive is identical between the two treatment groups. But of course, when comparing survival, we want to compare the function across all values of time. And we can see for the majority of values of time, survival is best for those patients on treatment C. So I would say survival is best for those patients on treatment C. Now we can quantify this in another way. The area under the survival curve up to 5 years is greater for those patients on treatment C. Now the area under the survival curve happens to be the mean survival time. In this case, it's the restricted mean survival time because it's only up to 5 years. So the mean survival time up to 5 years is greater for those on treatment C. So treatment C is associated with the best survival. What happens if we extend follow-up? Well, we see after 5 years, the survivor function is highest for those on treatment A. So, which treatment is associated with the best survival? Well, it differs according to follow-up time. And this is one of the features of the survivor function. It's a function of time. So differences between survivor functions for two groups can depend on time. So which of these treatments would you want for yourself? Well, it depends on what part of the follow-up time you're looking at, which could depend on what is your expected remaining lifetime. For an elderly individual who didn't have a long expected lifetime, you might prioritize early survival. For a young patient who has a long expected lifetime remaining, you might be looking more at long-term survival. But this is dependent on the situation, but from a statistical perspective is that the difference between the two curves may and often is dependent on time. Now, what if we look at the hazard functions? Now, I showed you the mathematics, but the hazard is proportional to the rate of change of the survivor function. And I hope that you can understand why this is. If the survivor function is dropping very quickly, then the patients are dying at a high rate. So a fast dropping survival curve means a high hazard. A flat survival curve means a low or zero hazard. So here are the hazard functions for each treatment group. Now treatment C actually has a constant hazard function, whereas treatment A has a higher hazard early. Now, you may have heard the expression proportional hazards. as in the Cox proportional hazards model, which we're going to look at later. Proportional hazards means that the hazard in one group is a fixed multiple of the hazard in the other group. This is an example of non-proportional hazards. These hazards are not proportional. Now, we often want a simple summary of the survivor function. I mentioned that we can estimate the mean survival time, the area under the survival curve. We can also estimate the median survival time. So the median is the time at which the survivor function is 0.5. So that is the time beyond which 50% of the individuals in the population are expected to survive. So here's an example on the next slide. This is not an example we've seen before, but if you go to the survival of 0.5, go across to the survivor function, go down, and here's the median here. So around about 40 months. So 50% of this population will survive 40 months or longer. All right, let's move on to testing for differences in survival between two groups. So firstly, what's some things which we shouldn't do? Well, we shouldn't compare survival at a fixed point in time, for example, 5 years. This wastes available information. We want to compare the curves across all values of time. What's particularly bad is look at the point of time where the curves differ the most and then do a test of two proportions there. Now, various tests are available for comparing the survivor functions, and the most common is the log rank test, which is the one I'm going to show you. This is a non-parametric test. We do not make any assumptions about the distribution of the survival times. Now, what we do, it's very similar to the table that we made when making the Kaplan-Meier estimates, and we make one table for each group. We tabulate the number at risk and the number of events, of deaths, at every time point. Now, under the null hypothesis that the two survival curves are the same, the expected number of deaths in each group will be proportional to the number at risk in each group. So let's have a look at an example for the AML data, and then we'll come back to this slide. So what we're going to do, we're going to compare survivor function between the two treatment groups, maintenance and not maintenance, and we see at time 5 months, we observed two groups, two deaths. So let's have a look at the data. So at time 5, there were 11 people at risk in the maintenance group and 12 people at risk in the non-maintenance group. Now, we observed two deaths. So conditional on observing two deaths, how would we expect these deaths to be distributed between the treatment groups if there was no difference? Well, we would expect them to be equally distributed, but because there's more people at risk in the non-maintenance group, we expect slightly more there. So the expected number of deaths will be proportional to the number at risk. If there was two deaths and we had 11 at risk in this group and 11 at risk in this group, we would expect one death in each group. So we continue tabulating the observed and expected deaths in this way. So at the next time where there were deaths, it was at time 8, there were two deaths, and here there's slightly more at risk in the maintenance group, so the expected number of deaths is slightly higher in this group. So we continue in this fashion, calculate the expected number of deaths in each group, Then we sum the observed number of deaths and the expected number of deaths in each group. Then we compare the total observed to the total expected in each group. And then we do a chi-squared statistic, test statistic, very similar to the chi-squared test for contingency tables. So I'm going to go back a slide. So here is the test statistic. Under the null hypothesis that the survivor functions are the same, this will be approximately chi-squared distributed with 1 degree of freedom. And here you can see the calculated value of the test statistic, and the critical value, the value of this test statistic beyond which we reject the null hypothesis, is 1.96 squared, which is 3.84. So we don't reject the null hypothesis at the 5% significance level. What we can see is the p-value is 0.07. So there's no strong evidence of a difference in survival between the maintenance and the non-maintenance therapy. Now, that was an example with 2 groups. If we have more groups, then it extends as we would expect. We just calculate observed minus expected squared divided by expected for each group, and then the test statistic has a chi-squared distribution with degrees of freedom equal to the number of groups minus 1. Now, it's difficult to apply the log-rank test while simultaneously controlling for potential confounding variables. A regression approach would be preferable, such as Cox regression, although in a randomized trial, potential confounders are controlled for in the randomization, so we can use the log-rank test to compare survival curves for the different treatment groups. Now, we need to remember the log-rank test provides nothing more than a test of statistical significance. It tells us nothing about the size of the difference. A regression approach allows us to both determine statistical significance and to estimate the size of the effect. Here's how we do the log-rank test in R. So we have our survival object, and then we apply the servdiff command to compare differences by our covariate X. And you can see these values here are the same as what we calculated previously. Here's our test statistic on 1 degree of freedom, and here's our p-value. In Stata, it's very similar. First we have to st-set the data, and then we say sts test X, and the output is identical. Now, I haven't shown you Cox regression, but many of you may have heard of it, and we can do the exact same test in a Cox regression model. Now, there's another lecture on Cox regression, but the difference here, we get the same test as the log-rank test, but we also get a measure of association. So here's our test statistic, very similar to what we got before, but we get a hazard ratio telling us the size of the difference. Here we see the mortality rate among patients without maintenance therapy is estimated to be this much, 2.47 times higher than the mortality rate in patients who did not get maintenance therapy. So we get the test statistic, we get a measure of the size of the difference, and we can very easily test for differences between one factor while adjusting for other factors. Now, here's the code in R, and R actually gives us 3 different sort of mathematical values of the same hypothesis test. We get the likelihood ratio test, we get the wall test, which is an approximation to the likelihood ratio test, and we get the score test. I'm not going to go over the math, but these are just three alternative ways of doing the exact same test. It turns out that the log rank test is mathematically equivalent to the score test in the Cox regression. So for observational studies, where we typically want to control for confounding variables, we don't use the log rank test that much. We use a regression modeling framework such as the Cox model. Whereas for a randomized trial, it's typical that you will see in the report of the trial, you will see Kaplan-Meier estimates of the survivor function and then the log rank test to test for differences. So that's the end of this first lecture on an introduction to survival analysis. In the next lecture, we'll look at Cox regression. Thank you.